Hello. So in this video, I'm going to present a different way of calculating coefficients for partial fraction decomposition than what we saw in class. So I'm actually going to use the same two examples that we did in our packets, specifically example 4 and example 5 from class. So you have one way of doing the partial fraction decomposition from class, and you can compare it to the method I'm about to show you to see which one resonates with you more. And of course, feel free to use either or both on future assessments, whatever strikes your fancy. So I'm not going to do the actual integration. I really want to focus on just calculating those coefficients for the partial fraction decomposition. So for this first example, okay, I'm already in a form where I have a denominator, polynomial in the denominator whose power is larger than the numerator, so the degree of the denominator is greater than the numerator, so I don't need to do long division. I'm already factored, just got to set up my partial fractions. So I'll do it on the side here. I have 2x minus 1 over x times x plus 1 squared. Now the start is the same. I mean, the decomposition itself is the same. So it's a over x. And then I have an x plus 1 repeated root, which means I need to do b over x plus 1 and a c over x plus 1 quantity squared. Now, to start solving, I should multiply everything by what? X times x plus 1 squared. So multiply everything. And what I'll be left with is 2x minus 1 equaling a times, so I'm going to have no, the x will cancel, but I have x plus 1 squared plus b times x plus 1 plus c times x. Okay. So now, what we've done in the past is simply plug in different values for x and start whittling down to solve for the unknown coefficients. Now, here is an alternate method. What we can do is expand everything on the right-hand side and start collecting similar terms. So I'm going to carry down my 2x plus 1 on the left-hand side. And on the right, I'm going to start just expanding out by distributing x plus 1 squared is x squared plus 2x plus 1 plus b times, and again, distribute the x, I'm going to get x squared plus x plus cx, okay? And then continue distributing, okay, so I'm going to get ax squared plus 2ax plus a plus, okay, bx squared plus bx plus cx. Okay, whew, so now I'm here. And now the key idea is to continue manipulating the right-hand side. I'm going to collect all of the like powers of x. So first, all of the x squared terms, I'm going to group together as x squared. And if I factor out the x squared, I'm going to have an a plus b left over, right? So I have an ax squared plus bx squared. Factoring out the x squared, I have a plus b in parentheses left over. Let me do the same for the x terms. So I have x's, x's, x's. And I'm going to group all of those together and then factor out the x that's common to all of them. So when I factor out an x from the terms underlined here, I have 2a plus b plus c left over. And then finally, I have just alone a, which is sort of the constant term. Okay, that's left over. And now here is the idea of this method. The idea is that these two equations, this equation can hold if and only if all of the coefficients on the left-hand polynomial and the right-hand polynomial agree. So let me quickly rewrite the left-hand side as, I want to do it a little bit differently. Let me write it as 0x squareds on the left plus 2x's minus 1. Right, I'm just rewriting that left-hand side, adding the 0x squared to be really clear about it. And on the right-hand side, I still have a plus b x squareds plus, I'm doing red, plus 2a plus b plus c x's plus a. And like I said before, the key is that for this equation to be equal, for these two polynomials to be equal, their coefficients have to agree. So I have 0x squared and then a plus b quantity x squared. For those to match up, I must have 0 equals a plus b. At the next level, if I compare the x coefficients, on the left I have a 2, on the right I have 2a plus b plus c. And then finally, at the constant level on the left, I have a -1, and that equals a. So what we're left with is a couple of equations that we can start solving and manipulating to solve for the a's, b's, and c's. So immediately I see a equals -1. I could always plug that into the first equation to say 0 equals -1 plus b, and so b equals +1. And now let me plug b equals 1, a equals -1. I'm going to plug all of that into the second equation. That gives me 2 equals 2 times -1 plus 1 plus c. And so in other words, 2 equals -2 plus 1 is -1 plus c, or c equals 3. Okay, so that tells me, so what are my coefficients? Okay, so x plus 1 squared. So that tells me that my partial fraction decomposition could be written as -1 times 1 over x plus b is 1 over 1 plus x plus c was 3 over x plus 1 squared. And if you compare to what we got in our notes from class, we got the same decomposition, but you see a slightly different method here. Okay, let me do the same thing for the last problem that we did together, example 5, just so you can see how that might work. Okay, so I've already done, if you remember example 5, we had to do a long division, and so I've sort of skipped over all of that stuff, gotten right to the meat of partial fractions time. So like above, let me start by writing 2x squared minus x plus 4 over, and now notice my denominator again, it's already it's a higher degree than the numerator, which means I don't need to do my long division. It's actually something we did earlier. But I am going to factor now. So this is x times x squared plus 4. This is irreducible quadratic time. So my right-hand side should be a guess of the form a over x plus bx plus c over x squared plus 4. Again, I need that bx plus c because of that x squared plus 4 is that irreducible quadratic. It can't factor. Okay. So now, like before, we're going to do the same sort of, clear the denominators by multiplying by the least common multiple, or the common denominator, right, of all these things, I should say. Okay, so x times x squared plus 4. And so now my left-hand side becomes 2x squared minus x plus 4 equals, on the right, a times x squared plus 4 plus quantity bx plus c times just x, okay, because the x squared plus 4's cancel. Now, again, instead of plugging in x values at this point, we're going to try the second method I just showed you, where instead we're going to distribute everything on the right-hand side and then recollect by powers of x. So 2x squared minus x plus 4 equals, distribute ax squared plus 4a plus bx squared plus cx, just distribute everything out. And then I'm going to go ahead and collect everything on the left, or sorry, everything on the right by their powers of x. So I'm going to get a plus b x squareds plus just a cx, it looks like, plus, and then a 4a. All right, so let's play the same game we just played. I'm going to compare the coefficients of like powers. So I know 2 must equal a plus b from my x squared term. I know, okay, here I have -1 x's on the left, and on the right I have 1c. And then finally, I have 4 constants on the left and then 4a constants on the right, which tells me 4 must equal 4a. Now look, I already have c is -1, and then that last equation quickly tells me that a is equal to 1. And if I plug that into my first equation, I get 2 equals 1 plus b, or it looks like b equals 1. Very nice. And so that gives me my final decomposition is 1 over x, so that's my a over x plus bx plus c, so that's 1x, 1x, what that? Let's write an x, 1x minus c is, plus c is minus 1 over x squared plus 4. Da, 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 da. Okay. And again, that should be the same thing we got in class. Yes, and it looks like it is. Wonderful. So here's a quick takeaway from this different method. The way I see it, so both methods that I've shown you now will work all the time. What you might have noticed is that using this method of collecting terms and comparing coefficients, this actually made the first problem harder than it was in class. I think this is actually a more complicated version of solving for coefficients in this case. But for the second problem I've shown you, this was actually a little bit easier compared to what we did in class. So it's hard to say that one method always is better than the other one. With experience, right, you could sort of practice these and get to this stage and say, oh, this looks like I could maybe do this method or I should use the other method. But again, it's up to you and both will always work. So I want you to see this so you could use this if you wanted to. You have the freedom to use it. But like I said, what I taught you in class will always work. Let me know if you have questions either way, and I'll see you in class next week.